Okay, so we are still on topic three. So it's still regarding heat and insulation. So we where we left off is on thermal insulation lah. Okay, so a bit on your assignment. So since you guys haven't take not sure if you guys got the subject regarding drawing or not. And then since the assignment also mentioned a bit regarding drawing, so let me just quickly pop it up. Where's the assignment? Yeah, here. So in your assignment here, here, this SRI. So this one is the topic two. So this section it mentions elevation view. So what it means by that is something like this lah. Elevation view. So elevation view is some sort of like a cross section of a material, and then this way is how you can showcase what's the material inside the wall. So you can have this frame, or you can have a board, insulation, and then inside you can have brick. And then if you want to go more detail, then here we can have plastering, and then maybe you can have wallpaper inside. So just an example lah. Doesn't necessarily have to be the same like this. You can search around lah and find out how is it like for different building. So this sort of particular example is more towards the US ah. So in Malaysia, we don't really see much of sheeting or boarding and stud frame. So what we have in Malaysia is we just have a piece of brick, and then we have plastering. Then that's it lah in Malaysia most of the case, because we are only dealing with one weather. So why do they have a lot of layer? So this is more towards thermal insulation, because there's four different season, so there will be a variety of temperature all over the year. So that's why to ensure that they are able to keep their home warm and also their home cool during the different season, to prevent heat from escaping or going into their house. So that's why they have so many type of layer. Whereas in Malaysia, we only have one single layer lah, if you say for wall. But then when it comes to our roof, then we will have this fiberglass. So it's a bit of difference between how the thermal insulation is done for in Malaysia and also in the other country lah. Okay, so a bit of a bit on the drawing. So since you guys will be touching a bit on building, so let me just go a bit on the different type of drawing lah. This will be a good example. Okay, so if you can see it over here. So when it comes to drawing, you can have this top, front, or side. So then here it can be also named as a plan view lah, or elevation view. So when it comes to drawing, we can have different type of name for it lah. And then here, this one we can call it isometric view. So it's a 3D view lah of the object. And then if you see it from the top, then we can call it this, or we can call it like this. So plan. elevation, and then if you see it from this angle, we get something like this, and then we call it front, or we have a side. Then we view it from here. We call it this, and then if we view it this object in a 3D view, then we call it something like this. So just an idea lah on what it means by different type of view when it comes to construction. So another thing, if you notice, this one will be able to showcase on a lot of how a drawing will look like. So we can have this will be rare lah. What usually we will have is something like this, maybe a top view, a cross section view. So this is what we call a section view. If you it's not clear, and then we can have a cut through section AA, meaning we cut through this object. So we can have different type of view on the object, and then we can have you will have all the dimension, and then finally you have your title block lah. So to be very to look formal and professional, usually the drawing will come with a title block, meaning they will have from who, and then prepared by who, worked out by who, and then they'll have some ID value, and then they have a scale. So this is how a typical drawing will look like, a typical construction drawing. But this is not for building lah. So this is for more on the M&E parts. So just an example lah on how a typical drawing will look like. So let's have a look on, let's say for a building. Okay. Bit small. Okay. This bigger. Okay, so this is still blur. So this is how a typical drawing lah, let's say for a building looks like. So usually you see it from the top, and then you have all the dimensions to showcase you how big is a room and everything. And then you can have indication of, is this a first floor, basement, and then you have other more pages lah to indicate how the arrangement of the other floor will look like. And then also you can have legend, because you won't be drawing everything. So you can put symbol to indicate what sort of items is in the room. And then you can have some notes. And then finally you have your title block. So this one is a bit of letting you guys know lah how a drawing should look like. But then since you guys didn't learn about it, so as long as you show me something, or you just show me this, I will accept it lah. There's no minus or mark or anything. But if you go above and beyond to showcase me something like this for your assignment, then definitely the mark will be better lah. Okay, so as long as you show me something like this, then you'll be good enough. But if you can include all of this title block and everything, then it will be better lah for the assignment. Okay, so continuing back to your topic 3. So this is, we are still regarding heat. So when it comes to building services, we want to ensure that we are able to keep heat out from the building if it's a very hot weather, or you are able to keep heat in when it's a cold weather. So why do we want to do that? Is because of the nature of heat. So heat will always be constantly moving from high to low. So when we have a cold temperature, then heat will always want to escape from our house. And then this is the case in reverse. When we have a hot temperature like in Malaysia, then we want to keep the heat energy out from our house so that it's cool during the day time. So that's why we want to have a thermal insulation lah. So this thermal insulation will be there in place to ensure that there's no exchange or there's a reduced exchange of heat in our environment. So always remember the characteristic of a heat is that they will always want to move from high to low. So they want to warm up all the area in the surrounding. So that's why we want to make use of thermal insulation to ensure that there's this reduction in heat exchange. So if we have a very good heat insulation, then our building will stay cool a lot for a very long period of time. So this way we don't have to crank up our ventilation or our aircon to make sure that our building is very cool. So if it's not well insulated, if our building is not well insulated, then we will feel very, very hot, or we can even feel even hotter than what is felt in the surrounding due to improper insulation of a structure. So imagine if your building isn't built properly or thermal insulation is not taken into account for a building, then instead of having a very cool building, for example, we use Malaysia as a condition, meaning the weather is hot and then we are staying in a building. If the building is not well designed, then it will become like oven. So heat will be absorbed very, very rapidly and then it will act like an oven. Then that is a very poorly insulated structure lah. Meaning instead of preventing the heat from going into the building, it's actually heating up the house more than more making it hotter than what is available outside. So this is important lah in the case of why we want to implement a good thermal insulation in a building. So we don't want to spend a lot of money to cool down the building. If you have a good thermal insulation and ensure that the building doesn't act like an oven when we are occupying it, then we don't have to waste a lot of money putting in all these ventilation service or air conditioning service inside the building to ensure that the building is at a very comfortable temperature. So there's also another factor when it comes to heat in our air. In the air surrounding us, we have to deal with this condensation. So depending on how humid our weather is, we can actually feel the difference in the heat energy. So humidity in the air actually correlates with how hot the heat is. So this one we will talk more about it lah on the next part. But do note that humidity and heat, they are actually relatable. Okay, so what is a good insulating material? So basically, a insulating material, a thermal insulator, is a material which opposes the transfer of heat between different area. So what the best material is porous and low density. So what if it's a material with a very high density and they are not porous, meaning you have a square, you have a block of material, very dense and very heavy. Let's say metal. So metal, we know that is a very dense material and is high in density. So metal is not a good insulator lah, because it's very good at keeping heat energy. So it's a very bad insulating material. What about plastic? So plastic, although it's not very porous, but it's actually low density. So heat doesn't really be kept into it. So plastic is a good insulating material. So that's why you have a pot. Let's say that's why you have a pot where the handle of the pot is made of plastic. So this way you'll be able to grab the pot and not have any transfer of heat onto your hand. Okay, so an idea lah behind the important part is this material for insulating, for thermal insulation, is porous and low density most of the case lah. So remember that heat can be transferred in three ways, which is convection, and then you have radiation, and then also you have your conduction. So we can have heat transfer in three ways. So to prevent that, we want to have a thermal insulation material in place to prevent all of this. So when it comes to air, air is actually quite a very good insulator, but there's a condition behind it. It's only when the air is not moving, meaning they are still. So that's why when it comes to, if you remember the previous topic, when it comes to noise control, we have a table of, let's see, is it here? Yeah. Hmm. Yeah, we have something, you have a table of something like this, meaning cavity. So we have two layer of brick. So a cut of the cross section of this. So let's see. So this is a cut, a cut across the wall. So we can have a brick here, and then we can have another air gap, or we call it cavity, and then we can have another brick. Oops. Okay. Hopefully you get the idea lah. So cavity or air gap, when you put different layer there, it acts as a barrier, not just for noise but also for thermal insulation lah. Meaning when it comes to having a lot of layer in between the exchange of this thermal energy, then we will be able to effectively restrict the transfer of this heat energy. So this is where the porous comes into play lah. If the material have a lot of air in between, then air is actually not a very good, not a very good heat heat transfer. So it doesn't really transfer so much heat over lah. Okay, so then we have radiation, heat transfer by radiation. If it cannot readily absorb or emit heat, so for this, you want to have a surface that is darker in color, because as we know in lighting, surface which is darker, they tend to absorb, and then surface that is bright or shiny, they will reflect away the heat. So it depends on how we want to do it. So here, shiny surface would reflect away the heat wave. So you want to have a shiny surface, but then if you have a shiny surface, it will come to another problem where it will be very blinding to the eye for people to look at. So that's why we don't have building which is very shiny. So we have a building which have a normal color. We don't have a black color building because black color will absorb all the heat into the building. Okay, so there's different thermal insulating material. So here we are shown five types of thermal insulation material. So one, we can have a rigid material, which is aerated blocks. So what it means by aerated blocks, meaning we can have a concrete block, but inside there's a lot of air gap, meaning this is a low density material. So uh, it will be a lot lighter lah when it comes to, let's say, the density is lower because it's not so tightly tied together. Then it will be lighter as compared to the normal concrete block. That means there's more air inside this block as opposed to a normal concrete block. And then we can have a flexible material, fiberglass grid. Let's see. So something like this, fiberglass grid. So inside here, there will be a lot of air gap lah. So this is a very easy to bend material. And then it's also very soft and it have a shiny surface. And then we have a polystyrene granulates. Let's see. Then next we have a foam polyurethane, which is this. So this one is a foamy material. So this one a loose fitted. Maybe it's this. So this one is a spray on lah, the foam polyurethane. And then finally we have your aluminum foil, which is this. So all of this material, you notice one thing in them. They are low in density. So this one is not a metal lah. This is not a metal. Just so you guys know, this one is a glass. So this is also a glass lah, some sort of a glass. As the name mentioned, they have a glass in it. So it's not metal. The only exception is this lah. So when it comes to aluminum foil, instead of how they insulate, how they are different, although they are aluminium, they are part of a metal family. So what it does is not more on insulating, but it's more towards reflection of the heat energy. So it's not a very good thermal insulator, but when it comes to reflecting away the heat, then that this aluminum foil is good. But for the rest of them, they are more better in terms of insulating because they are low in density. So when it comes to heating up this material to allow it to allow for heat transfer to another area, then they are good. So these four are different. These four are different from this. So this is some sort of a metal. So they are is more towards reflecting rather than inhibiting the heat to transfer in between the area. Okay, so to to know or to understand the rate at which heat is conducted through a particular material, we have this thermal conductivity, and we call this symbol lambda lah. So the unit is watt over meter K. So there are, and then we have another thing is resistivity R. So this is just a inverse of this thermal conductivity. So the higher the value, the better it is the material at conducting heat. So if you see here, we have a normal concrete and we have a light concrete. The value here, this is the thermal conductivity. Because the normal concrete is denser as opposed to a light density concrete, lightweight, because it's lightweight. So that's why it has lower density. Then they have a lower thermal conductivity, meaning it doesn't conduct heat so well because it's lower density. So this is assuming lah, that they are the same size, meaning they are both one. Let's see, they are both 1 meter cube. Just for example lah. So they are both in 1 meter cube because of here. Just for example sake lah. So in a 1 meter cube concrete, for a normal concrete, they will weight about 2,400 kg, and they have this value of thermal conductivity. And then for a lightweight, or we can also call this an aerated concrete, then it will have a lower weight because the density is lower, and due to that, they are not as good as a normal concrete to be able to transfer the heat. So here, the fo- it shows three different factors which can affect thermal conductivity. So this will be important lah in your lab practical. So based on what I've just mentioned just now, if we have a higher density, then we have a higher thermal conductivity. That means this material is not very good in thermal insulation. So we don't want to have a high value lah. We want to have a low value for this. And then next, if you have any changes in moisture content, so if you have high water, and then this will cause heat transfer through conduction. So through conduction. So remember, conduction is the exchange of heat energy through the air particles, meaning heat is present or being held in the air itself, and then through conduction, they are able to very quickly transfer the heat energy from area to area. So let's see, as moisture content increase, the lambda value increase, and then insulation effect decrease. So this is a longer explanation lah. So when moisture content increase, the thermal conductivity increase, meaning there's more in the exchange of heat energy. So what is this telling us is that the air, when you have a lot of moisture or humidity in the air, because water is good in containing or holding heat, then insulation effect decrease because instead of the building acting as a barrier, the humidity in the building or in the surrounding air itself is carrying the heat energy. So this is how changes in moisture content can reduce our insulation effect of the building. Okay, so then finally we have effect of time. Okay, so when it comes to the effect of time, because all our material, when it comes to the choice of material, you'll notice that you use a lot of plastic. So we have glass, we have the polyurethane. All of them are under the family of plastic. They are actually very, very light, low density, and they are also porous if you look at it at a microscopic level. So they are plastic like material. So when it comes to this material, they actually deteriorate lah in performance as they age. So when they deteriorate or they start to decompose, when it come as the times go by, the thermal conductivity value increases over time. So remember, thermal conductivity is how good a material is at conducting heat. So when a material degrades, they will become better to transfer heat energy. So this one, a material, this is a picture showing how a material can transfer energy. So typically, when you have a high temperature here, if the heat is supplied here, it will heat up the material and it will travel heat from high to low. And once it reach here, then if the temperature here is low, they will go out. So insulation, or we have a material in place to ensure that if there's a high temperature here, it doesn't heat up this material and spread the heat into the building. So this is the idea lah in heat insulation. So next we have thermal insulation value. So this can be done in two. There will be two lah. The first is a thermal resistant, and then next is the let's see. Next is a thermal transmittance. Okay, so when it comes to thermal resistance, there are three items in a material that determine how good a material is in opposing the heat transfer. So we can have a material, we can have a surface, and then we can have a airspace. So this airspace is, as I mentioned, lah, the air gap or cavity, and then we can have a surface. So surface is more towards the plaster, wallpaper, and then you can have material. So the material is as seen here lah. We can have plaster, brick, and then you can have plaster and brick. So typically for Malaysia construction, what we have is plaster and brick. And then when it comes to surface, it's more towards wallpaper lah, or outside surface or inside surface. So depending on what sort of paint we use, we can consider that as our surface. So it can be a weather resistant or just a normal inner wall paint lah. So that is what we consider as a surface resistant. So all of these, when you add up together, they they represent a certain value of thermal resistance. So this thermal resistance can be represented by this formula when it comes to material, where we have R, which is the value of the thermal resistance of the component, equals to the D, how thick the material is, and what is the thermal conductivity of the material. So basically, you just divide lah the thickness with the thermal conductivity of the material. So this value will be given to you, and also this value will be given to you lah when it comes to if you have an exam. So this is a case when you have a material. Okay, so when you have a surface resistance, is also the same case. You also have a lambda value to just add together, and then the same goes for air gap lah. So to find a material thermal resistant or the thermal resistance of a material, you will have to add together the surface, the material, and the cavity. So higher value is better lah. So this is a resistant. Okay, so if you see here, this table, this is an example lah, of the different type of resistance for a material. So let's say, for example, we have a wall inside and outside. Inside surface, they will have this value of resistance value, and then when it comes to wall, then outside surface, they will have this value and this value. So depending on the surface, there's a range of the resistance value. And then when we have a air gap, then we also can have a value also lah in between. So all of this is just a table example to pick and plug into your equation. Okay, so coming to this, so next we have thermal transmittance. So because a building doesn't just made up of a single component. So in a particular wall, there might be window, there might be door. So all of these different material you need to add up together to make it to make it a single composite material. So sort of like the topic two lah, where we have the sound reduction index. So different material you want to make it into a single material. So that's why we have something like this. We want to make it into one area with one universal value. So how good the material, how good the wall section is at reducing the transfer of heat, then we particularly want to have something like this. Okay, so example 6 to showcase the what we have learned and make use of the formula that we have here learned. So U value of this cavity wall with this with 100 mm thick brick outer leaf and 50 mm of clear cavity and then 40 mm of insulation board. Then we have 115 of this concrete block with the inner leaf of 15 layer of light plaster. So we are given a lot of material and we are required to find what is the U value of this cavity wall. So this cavity wall has, let's see, so they have 100 mm thick brick, and then in between there's an air gap, and then we have a insulation board. Then next we have another concrete block, and then finally we have a very thin layer of plaster. So all of them, you'll be given the thermal conductivity. So based on that, you'll end up with something like this. So this is a cross section or elevation view of the wall. So this is what is required for your assignment. But when it comes to example, if you guys find it hard to remember or make sense of what the material is or how the material is, you can always take a very quick few seconds to work out the different layer like what I just did. Just quickly draw it. You can have a brick layer, air gap. Then this is the insulation, the plasterboard. Then you have another layer of brick. Then you have a plaster, and then you have any outside layer or inner layer. So once you work all of this out, basically when it comes to thermal resistance of the material, you can just multiply them together lah. So let's see. Okay, so you have surface resistance internal. You don't have to multiply anything because there's no thickness. It's a standard value. Same goes for external. Then for air gap, it's also the same. So the only thing you need to multiply is only thermal resistance for the material, which is D over lambda. So here, you're given the lambda for brick, insulation board, the aerated concrete block, and plaster for material. So here, you have your plaster, concrete block, insulation block, and then brickwork. So then you have your thickness. So this is all given to you lah. This one you can ignore because it's given to you as a standard. So you just divide them together, you get all this value. Then finally you add them together and you get a value of the U. You get a value of your U value, which is the thermal transmittance. So a building can have different material and object. This is the way lah to compute together how good is the resistance or the thermal transmittance of this building material. So finally, you want to use the formula lah, the U equals to 1 over RT. You work out the U value, which is this. Okay, so next is combining the U value. So when we have different area, we can use this formula, which is the average of this is called averaging of the value lah. So we can have an area and a typical value. So this formula is a max formula lah to average out what is the typical value. So this formula is very similar to your this in topic 2. Let's see. Yeah, so it's a composite formula lah, meaning when we have different material, doesn't matter if it's for sound or for heat topic. In this heat or sound topic, when we have different material, we can make use of this formula to get the average value of this whole material. So this is the same case on what we are doing here with this formula. So we can have different material. Then to average it out to get the whole value of this wall, we can have a window. We can have a window. We can have a door. So to average out all this value, we use this formula. So here, as I mentioned, for me, when it comes to calculation, for your work, if you want to have up to 3 or 4, is alright. But my minimum requirement when it comes to calculating is at least up to 2 decimal places. So any more than that is all extra lah. So I don't need more. I need at least 2 decimal places when it comes to calculation. Okay, so finally we have example 7. So let me finish this, then we go for a break. Then we continue on the next part lah. So we have example 7, calculating the U value. So what if in the case of we are given the U value, and then we are also given a insulation board, and then we actually want to reduce the U value, meaning we already have an existing building, but because it's uninsulated, so we want to add in extra insulation, which is the insulation board, to reduce the U value of this building to this level. So how thick of material we want to use to ensure that we can reduce the thermal transmittance of this construction. So we will have to make use of the formula lah. So first off, we have 0.45, which is a U value that we want. So we cannot straight away uh, work it out this thickness. So what we need to do is we need to convert it into resistance, the total resistance of the building, using the formula R equals to 1 over U. So we work out that the target resistance that we want is 2.22 and the existing is 1.09 using 0.19 lah, the existing U value of this wall. So once we work out the resistance, because when we work out the resistance, we will be able to, it's the same thing, but when it comes to U value, it will be a different thing due to it being a composite material lah. Meaning this and this is not the same. This and this, they are not the same lah, to put it in a perspective. But when it comes to resistance, they are the same item. So we will have to convert this into resistance first. Then once we get the value for the uninsulated and insulated U value of the resistance, then we can minus them off and we find out that the additional resistance required is this value. So with this value, given that we know the thermal conductivity of this spot, and because in this formula there's no D, so we want to make use of the thermal this formula, which is the resistance of the material. So using this formula, R equals to D over lambda, you'll be able to work out the extra thickness of the material required to insulate this cavity wall to the thermal insulation value that we want. So we have this R, which we can just put it into here, and then we have lambda, which is given. So we work it out, you get one value. So do note that this value that you got is in meter. And then with that, you convert it into mm, you get 28 mm. So this is the idea on why you want to work out this example in this way. The U is not the same thing, but resistance is the same thing. So you need to convert this into R first. Then once you minus them out, you can use another formula to find out what is the thickness required to get the additional level of resistance required. So once you work it out, finally you get this value. This is in meter lah. Make sure you convert it, and then based on what the example or what this question asks, then maybe you need to give additional comment or what. But if you read through this question or this example, it didn't mention anything lah. It just asks what's the minimum thickness, so you can just put it like this. Then it'll be good enough lah for this example. Okay, so next we have one more. Okay, bear with me. We can have example 8. So we can combine the U value. So this is basically just using the composite formula lah to work it out. So you can have a 3-bedroom with 20 meters square, and then you have a mixture of 16 meters square double glazing, and then 4 meters square single glazing. So this glazing is, if you add up together lah, 16 and 4, they are 20 meter. They are actually glass lah. So this is glass. This is 16, 4. They are all glass. It's just the insulation layer lah of these glasses. So this glazing is called is the insulation of these glasses. So if you add them together, they are equal to 20 meters square. They're actually part of the glasses. Okay, so then this 16 meters square, the double glazing, they have this U value. Oh, sorry. This 1.8 is for single glazing and sorry. This 1.8 is for double glazing and then this 2.8 is for single glazing. So based on these two different insulation material applied to this glass, we are able to use the composite formula to find out what is the average U value. So you're given this and this. So this one is double, and then this one is single. So what can we do to get the average value of these glasses? Because we have two different value, we use the composite formula. So 16 and 4 here, and then you have 1.8 multiplied by 16 plus 2.8 multiplied by 4. So you put all the formula in, you'll be able to get the average value of this U value for a single component. For now, we are doing it for just this wall window area because they have something like this. So this part might be, just an example, this part might be single glaze and then the rest will be double glazing. So this gives you an idea on how a thermal insulation calculation can be like. So this example 8 showcase a small window, but when it comes to bigger scale, we can have a lot of material. We can have door, we can have more window. So when it comes to calculation, we want to ensure we capture the whole surface of the wall the whole wall because the sun is shining onto here. And then depending on if you have a second floor, then we have another set of calculation to make to check to ensure that the building is not very good at becoming an oven for us to live in. Okay, so I think let's have a break here. Okay, maybe I can finish off this and then you can have a break here. Hopefully, we can finish this and then we'll stop. Hopefully, let's see how long it will take for this. Okay, so let's have a break, 15-minute break.